let's look at the first categories, the first type of radiation. If you have proton higher, the number of protons is higher than 82, there's nothing stable. So you have to release the proton, because proton inside the nucleus, they have electrostatic repulsion, right? So if you have so many protons inside, so electrostatic repulsion is so strong. So what we can do is just kick out some of protons from the nucleus. And yeah, from the choices over here, what you can do to release it as quick as possible, because you have so many protons, right? So you have to get rid of them as much as possible at once. So the particles that can release a lot of proton at once is the alpha particles, because alpha particles is actually the nucleus of helium, as you can see here. So that means if you have huge particles, huge nucleus, it just releases the proton out, okay? And the size of the nucleus is getting smaller. So what you can have here is helium-2 plus. Okay. Why it have to be helium-2 plus? Because, as you know, from belt of stability, from everything, the smaller atom required N to P, N over P ratio, less than the bigger particles. As you can see, the small element like lithium, helium, boron, carbon, nitrogen, neon, things like that, you normally have the same number of proton and neutron together in the nucleus, right? Carbon 6, 12, right? Or oxygen 8, 16, neon 10, 20, right? So you have the same number of proton and neutron. So if you increasing up the number of proton like this, the polonium, as you can see, you have a lot more neutron in the structure, in the nucleus. So it requires higher number of neutron. So if you reduce the size of the nucleus by getting out, take some of proton out, that means some of the neutron is not necessary anymore, because you release the proton out, right? So it's less number of neutron required to stabilize the nucleus. So you better release both neutron and proton all together. So this is why you produce helium-2 plus as the product. Okay? So if you're starting from the polonium-84, right? So after release of alpha, right? Helium is actually the alpha, right? So after you release alpha particles to 4, okay? So what happens is the number of proton inside the nucleus release, right? Reduced down for 2 units. So at the end, you have the number of proton just 82. And then the name of element is changed from polonium-84 to be the element number 82. And the element number 82 is lead. Right? So you have lead as a product. And because you released 2 proton and 2 neutron, so the mass lost is 4 units. If you lost 4 units of mass from 210, it reduced to be 206. So this is the first kind of radiation, the alpha radiation. So the radioactivity happens because you have too many proton in the nucleus. So you have to release out the proton. And by releasing proton out, you require less number of neutron. So you kick out both neutron and proton all together as much as possible. Yeah? So it has to be helium. Okay? So as you can see here, first of all, you have very high electrostatic force here in the nucleus because you have 84 proton. But now you release down, right? You release them out, you have less electrostatic repulsion force. So that means the energy, the potential energy of the nucleus here is higher. The potential energy of the nucleus here is lower. So whereas the extra energy, right? Because you release the energy out, okay? So the energy in the nucleus is decreasing down. So where the extra energy is transformed to be kinetic energy for alpha, right? So you kick out the alpha, go very fast, right? Near the speed of light, okay? Get off from your nucleus by the kinetic energy that's transformed from the potential energy in the nucleus. Now, if your element is above the belt of stability indicates the optimum or suitable NOP ratio. If it is above the belt, that means NOP ratio is too much, right? So it is too high for NOP. If NOP is too high, what you can do is decrease the N and increase the P, right? Decrease the N, increase the P, meaning that you have to transform neutron to proton. This is how you can really decrease down that value and increase up this value. So NOP drops, right? So if it is above the belt, that means NOP is too much, right? Drop down by this kind of thing. So you have your atom come down to the belt, nearer to the belt. But yeah, you have to conserve mass and charge over here. So the mass is 1 and 1. So the particle released from this reaction would be 0 of the mass. And for the charge, this is 0, neutral. If you produce positive, you also have to produce negative charge in order to neutralize, right, or conserve the charge from the system, for the system. So in here, what you can see is if your element is sit above the belt or you have too high NOP ratio, you have to decrease down NOP ratio by decrease N and increase P. So you transform N to P and you have to release something negative charge with no mass, which is actually the beta minus or electron. So electron is a byproduct from this. Okay. So if you're starting from carbon 14, because carbon 12, you know that carbon 12 is stable. And if you know that carbon 14 is not stable, you have to compare with the stable isotope carbon 12. So carbon 14 differs from carbon 12 because you have extra neutron. So that means this shall not stable because you have too much or too many neutron in the nucleus. So in this case, you have to get rid of neutron, transform your neutron to proton. Okay, so by this kind of thing, you release the beta minus 1, 0. So your neutrons transform to protons. So the total number of protons in the nucleus is increased from 6 to 7. So change from 6 to 7. And as you can see, the charge is conserved. 6 positive is equal to 7 positive with 1 negative, right? So the charge is conserved. By change the number of neutrons from 6 to 7, that means the element is now changed from carbon to nitrogen here. And because neutron is changed to be proton, so the mass is equal. Because mass of neutron and mass of proton is equal, right? So if you start from 14, you have to end it with 14. 6 proton, 7 neutron. 6 proton, 8 neutron. Now you change neutron to proton, so it's 7 proton and 7 neutron. 7 proton, 7 neutron weighted 14. Right? So from unstable isotope, high energy isotopes, you change it to be stable isotope or low energy isotope. So extra energy go out with the electron here. So electron was kicked away by that kind of energy, right? Or transform that energy to be kinetic energy and release it as beta, go very fast out by near to the speed of light. So this is when you have the element with very high NOP ratio. But if you have very low NOP ratio, or your element is sit under the belt, you have to push it up to the belt, right? So as you can see, if you have too low NOP, you have to increase the N and decrease the P. So to decrease the P and increase the N, you have to transform your proton to be neutron, like this. Okay. And to conserve mass and charge, The mass is now conserved, the charge is not. It's not. So from positive charge, you have to product with neutral. So that means you have to create another product with a positive charge. And is the antiparticle of electron, which is called positron. Right, positron. So for example, cobalt. There are three major isotopes of cobalt in nature. Cobalt 58 is only a stable isotope. Cobalt 59 is the only stable isotope. 58 is not stable, 60 is not stable also. Okay, but for different reason. 59 is stable, so if 60 is not stable, it's not stable because you have extra neutron. So 59 is stable. 58, if it's not stable, it is not stable because you have less neutron than the stable isotope 1. So what you have to do is you have less neutron. You have to produce more neutron by just transform proton to neutron. So if the proton is transformed to neutron, you release the beta plus, right? So the product here is the beta plus, right, or positron. So if you create a beta plus by transform proton into neutron, so the number of proton is decreased down 1 unit from 27 to be 26, and the 26 is the iron, Fe, ferrum. Okay, and because proton is transformed to be neutron, so the mass is conserved. So 58. Okay, that's it. Now, from high energy nucleus, you have stable energy nucleus here. That means the energy level decreasing. So the extra energy goes with the positron. So that means your positron is kicked out, right? So it's fly out very fast, very quick by that kind of energy transformation. Okay, this is 3 of the phenomena from instability isotopes. But sometimes like this. Okay? As you know, when the nucleus is not stable, and then you make this kind of transformation, you have lower energy state of nucleus. Okay? This is high energy by the electrostatic repulsion. You have less electrostatic repulsion. This high energy because NOP is too high, right? So you decrease down. This is high energy because NOP is too low, you decrease down. So extra energy go out with the particles here as kinetic energy. Right? But for iridium here, the energy of the iridium is not very high. It's not stable, it's high energy, but the energy here is not high enough in order to kick away beta plus. So if the energy of the unstable isotope here is not much, is not high enough, what can happen is instead of release proton out, the transformation between proton and neutron would be something else. So instead of release something out, the thing is your proton gonna recombine with something and creating neutron. Okay, so what shall be this one? Can you guess? And if you can guess this one, you can then finish the reaction here. Okay, I will give you 1 moment for doing this. So pause the video here. Okay, if you finish, continue the video. So to transform proton to neutron, right? Again, the rules is the rules. You have to conserve mass and charge. So proton have to recombine with something with mass number equal to 0 in order to conserve the mass. And in order to conserve the charge from 1 positive, you have to recombine with something negative in order to neutralize it, to form the neutron with no charge, right? So the particle that have to be recombined with the proton have to be negative, 1 minus and 0, which is the electron, right? So your nucleus, proton in the nucleus, have to recombine with an electron. And the nearest electron that can be recombined with the proton is the electron in K shell. So in this type of thing, we call K electron capture. Electron capture or K electron capture or K capture, whatever. Okay, so your iridium gonna take one electron from the K shell, and then it's transformed. So after you take one electron here, recombine with a proton, producing neutron. So the number of the proton in the nucleus is reduced down 1 unit from 77 to 76, and this is a new element called osmium. Okay, osmium. And the number of proton and the mass of proton and neutron are equal, right? So the osmium here is osmium 1I1. Okay. So this is electron capture. So actually, if you have too low N over P, there are two alternatives, right? Subcategories. There are two alternatives. You can release positron as a product, or you can have electron captured, right, by the nucleus. Proton in the nucleus, capture one electron and transform the proton itself to be neutron. This is another possibility. It actually depends on the energy in the nucleus, how unstable it is. If it is very unstable, very high energy, you can release positron. But if it's just a bit higher, so what it can do is you cannot kick out heavy things like proton, electron, positron, right? So it captures something inside. But look at this. This is unstable. That means the starting material here is high energy. And yeah, it has to be lower energy. In this case, from cobalt to iron, energy of the nucleus is decreased down. And the extra energy goes with beta plus, right, as kinetic energy, release it out. But now, you cannot release things. You cannot release the energy. That means the energy is still here in the osmium nucleus. So the osmium nucleus is in the excited state. So I just put the star over here to say that this is the excited state of the nucleus. So that means after transformation from iridium to osmium, the energy is still there. Even though the ratio of neutron and proton of osmium bring the energy down, but there's no way to release the energy of the iridium at the starting point, right? After it transformed to this. So energy is still here, right? Accumulate here. So what can happen is your osmium can then release this kind of energy out just as radioactive radiation. So without any particles, it's released as photon, as radioactive radiation. So it's just like reduced down the energy level from excited state to be more stable. So you just have to release something else, some energy out. So this this electromagnetic radiation is called gamma. So it's actually A, B, and C, alpha, beta, and gamma. That's that. Okay. So your osmium release the energy out as electromagnetic radiation gamma ray, and that's it. But actually it's not over yet, because if you look at your iridium, right? Your iridium composed of proton and neutron, things like that, in the nucleus, and you have electron in K shell, L, M, N, O, P, things like that. So after you have electron captured back down here into the nucleus, that means you have a vacant site in K shell. And you know that electron and proton, you have very strong attractive force between positive and negative charge. So the positive charge proton nucleus, right, will drag electron back down to the K shell. So if electron drop from L shell is empty, right? You have one site available, one orbitals available. So electron have to drop down a bit from M and N and O and P and so on. So that means at the end, right, electron will drop consecutively from the outermost shell back down to the K shell. And by releasing of energy of the electron from the outermost shell down to the K shell over here, it will release the energy out in the form of electromagnetic radiation again. And the electromagnetic radiation from this electron relaxation is called X-ray. X-ray and gamma ray is in terms of energy levels, they are quite the same, but they come out from different mechanisms. Gamma rays come out from the nucleus, right? But X-ray come out from the electronic transition over here, right? So these are the four types or five types of radioactivities of your radioactive element. Okay, but sometimes sometimes radioactivity is not very simple like this. Right? Let's look at something very big like uranium number 92. Uranium number 92 release out the alpha particle for sure because the number of proton is 92. Even 84 is not stable and you have to release alpha particles. So if you're starting from 92, you release alpha particles, you still have very high number of proton, right? From 92 you have 90. So that means only elimination of alpha particles, one alpha particles is not enough to bring the things back down to the stable state of energy. So sometimes one particular element or isotopes have to release more than one type of radioactivity here to make things stable. Okay, so there are a series of decays of radioactivity from one element until if you're starting from uranium, as I said, you require a series of radiation until you can drop the number of protons from 92 to be less than 82. So now we will see that kind of thing. Okay, as I said, that sometimes radioactivity, just one step is not enough to stabilize all the things. For example, this element, I'm starting from uranium number 92. The graph is plotting on x-axis is the number of proton and on y-axis is the number of neutron. So as you can see from here, uranium is dragged down here, 88 here, 90 here, and 92 here. So uranium is number 92, and the number of proton, so it is 36, 38, 40, and then this is 41. So 141 plus 92 is 233, right? This is the number of neutron, number of proton, and the mass number over there. So if you look at this uranium, let I show you here. Uranium 92,233 with the number of neutron is equal to 141. So N to P ratio, I would draw it like this. Uranium 92,233, right? So N to P ratio of this uranium, I need to use the calculator. So is 141 divided by 92, so it's 1.53. Is 1.53. Because uranium has too many protons in the nucleus, it's beyond 82. It's beyond the late. So it's not stable. It decomposes by eliminating alpha particles, release out 2 proton and 2 neutron. So release 2 proton, you have only 90 proton left in the system, and then release out 2 neutron as well. So the mass number released down for unit, it would be 229, yeah, and 229 over here is your thorium. So is that one. So from the graph, moving down here is releasing of particle. Okay, and if you look at the thorium here, the number of neutron is about 139, right? It's 139, and then if you divide with the number of proton over here, 90, it is 154. 154. What happened is, by releasing of particle, the N over P ratio is increasing, obviously. Why? Because if you remember the belt of stability, right? It's something like this, okay? But what you're doing here, uranium is somewhere around here. And you release proton and neutron all together, 2 and 2, 1-to-1 ratio, right? So it's 45 degrees decreasing down in this way. So decreasing down like this, it moves your isotopes to be beyond the belt of stability. Because decreasing down the size, the number of neutron and proton required is less, right? But you release N and P in 1-to-1 ratio. So at the end, N and P is increasing and it is higher than usual. So if to make it more clearer, release again another alpha particle. You transform thorium to radium because you lost 2 proton and the number of proton will be 88, and 88 is radium, and the mass number is 225 because you lost 4 units of mass. And for the radium here is 137 divided by 88. You end up at 156. As you can see, the N to P ratio is even higher, right? So the element getting smaller, normally from belt of stability, the element with smaller number of proton required N to P less than usual, less and less, right? So, but NOP here is getting increasing. So at the end, NOP is too much, like this. So if NOP is too much, right, we've already discussed about NOP is too much. What we have to do is just like to make beta irradiation. So if you have beta radiation, transform N to be P. That means you release, you reduce our NOP ratio. No. So if NOP is too much, just cut off the N and increase the P. So you transform N to P. Transform N to P from neutral to positive. You have to release something negative. So this is why you release the beta minus particle. So that's, you transform N to P. That means the number of proton is increasing from 88 to 89. And the element changed the name from radium to actinium. Okay, but the mass is the same. But now, because you transform neutron to proton, then the number of neutron is decreased from 137 to 136, and then divide by the number of proton, 89. Now your N to P ratio decreased to 153. Okay. So NOP is relaxed, right? So NOP is getting better, but still the number of proton is still very high. So what happened is you have to continue eliminate the alpha particles. So in each step you have to eliminate whether alpha particles or beta particles. You release alpha particles down until NOP is too high. Then if the NOP is too high, you have to release the beta particles and then continue alpha particle for several times, and then if NOP is too much, you have to do beta radiation again. And things go on until you have something less than 82, and that's it. Stop the radiation, right? So it's the decay of a radioactive element is come in series like this. Okay, and that's it. I will give you one more examples, okay, for you to finish, and then we'll end this topic. So this is another assignment for this topic, the radioactivity. So if you're starting from the thorium, mass number 232, and then undergoes radioactivities, okay, and still the end product, the very final end product is late number 82 with the mass number 208. The question is, what is the radioactivity created here? How many alpha, how many beta, things like that? Would it eliminate only beta particles or alpha particles or mix of alpha and beta, things like that, how many of each kind of particles. Okay? And another question here is we're starting from uranium. Okay? And look at those 14 steps of decays until we reach to late, but in the isotope of 206, okay, with 14 steps. So what is the mass number of the starting uranium? Okay? So I have here two questions. Okay? So pause the video at here again and use everything we have discussed before here, okay, to answer these two questions. Okay, good luck. So if you finish the assignment, now I have to give you the answer. Because as you can see before here, each steps of radiation, you lost maybe alpha or beta by the theory behind it I already described. Okay, so in this case, starting from this to this, actually it's not only one step, it has so many steps, right? And each step, there is just only two possibilities, alpha particles or beta particle. The alpha particle is 2, 4, the beta particle is minus 1 and 0. Okay? So we have two factors, A and B, two variables. Okay? And yeah, we want to know two variables, so we have to construct two equations. Okay? And because the mass have to be conserved and the charge have to be conserved. So we play with the mass first because the mass number of this is 0. So we can make up the equations easily. So first of all, at the mass, 232 have to be conserved. So the product mass, total mass of the product have to be 232 as well. One of the product is 208. Another product is alpha. We have A particles of alpha. Each particle is weighted 4 units. But beta particles has no mass, so you don't have to use that. We have only this. So move here to here, you have like 24, right? 24 equal to A4. So at the end, the A is equal to 6. So after you have A equal to 6, then you can play with another equation by the charge, the conservation of charge. The charge of the starting material is 90 plus, right? So the total charge of the product has to be 90 plus as well. The charge of the late is 82. The charge of the alpha particle is 2. But you have 6 particles of alpha. Each alpha particle have 2 positive, right? And then you have B particles of minus 1 of the electron, right? So 82 and 12 here, 82 and 12 is 94, right? So you move it here, so minus 4 will be equal to B minus 1, so B is equal to 4, and that's it. So in the first question, we can then now know that the process to transform thorium to lead, you have to undergo for 10 steps of decays, and all 10 steps, including alpha radiation for 6 times, and then beta radiation for 4 times. But you cannot know which alpha and beta, which one can happen first, second, and third. No one can know that. Okay, but roughly we know that there are 10 steps. 6 steps for alpha radiation and 4 steps for beta radiation. So after finish this, if you struggle with a bit about that, now I give you the answer. Now you have to know how to solve this question. Okay, so I leave this to you again. So pause the video here. But if you finish, now play with me. So here we don't know this number. We put X here, but we know it's 14 steps, right? So if we know that it is 14 steps, what we can put here is actually you release some of the alpha of 2, 4 and some of the beta minus 1, 0. Okay. So if this is 14 step, that means if you don't know, this should be A again, and this should be B, right? But B here is actually 14 minus A, right? Because in total there is 14 steps. So if it is A step to release alpha, it has to be 14 minus A to release the beta, right? So from here you can set up the equation. So now we have two equations. The equations of the mass and the equation of the charge. For equation of the charge, number 92 here would be equal to 82 positive plus A step of 2 plus and B step of 1 minus. But B step here is 14 minus A step multiplied with minus 1. So actually this is this can be calculated as 92 equal to 82 plus 2A plus, minus 1 multiplied with 14, no? It's minus 14 and then plus A. Okay. So from here, if you move 82 back to left hand side, it's 10, right? And move 14 to the left hand side, 14 and 10 is 24. So 24 is equal to 3A. So this means that the A is equal to 8. So if you have A equal to 8, that means B would be equal to 6, right? Because A and B summation have to be equal to 14 because you have 14 steps, right? So alpha for 8 particle, beta for 6 particle. So after you finish this, you can find the x right away because the x is the mass and the mass have to be conserved at x. X would be equal to 206 and then plus 4A, and the A is 8. And plus 0 multiplied with B. 0 multiplied with 6 is 0. So this is it, right? So 32, no? 206 plus 32. So 32 and 206 is 238, right? So that means the starting isotope of the uranium is a 238, and that's it. Very common. So that's all about the radioactivity, right? So now we know the radioactivities. Next step, we're gonna look at how we can make use of the radioactive filament. Okay, so going to look at the applications of radioactive filament in the next clip.